All right, yeah. So previously we learned about the buffer overflow and then control flow hijacking attack. And the reason why we suffer the program suffers the buffer overflow attack is like it gets more bytes than like the buffer should be. And also like because the buffer is adjacent to some of the sensitive data, so-called control data, including the saved AVP, this frame pointer, and also the return address. And then even if they implement some of the security measure, countermeasure, they place a stack cookie near there. And now we know that that's not a good design at all. Yeah. So there are many kind of the attacks that we can do. Yeah. And then generally, so buffer overflow is actually a single instance of a control flow hijacking attack. So the reason why I'm explaining this is like so we started learning hacking about like the buffer overflow, but this is just a single instance, specific case, but that there could be a general version of the idea that can be applied to many other attack surfaces. And the general category of the buffer overflow attacks, in the upper level, we call it as a control flow hijacking. So from the name says, all the attacks that we try to divert some of the control flow of the code to execv BNSH. Yeah, these are all falls into the control flow hijacking. So not just for like the diverting the control flow to our shell code or something, if we can divert from one function to the other, if that is an unexpected behavior of the program, then that is control flow hijacking. So it could be return to some other function, return to shellcode, return to ROP gadgets, all falls into the control flow hijacking. And then the method is somewhat simple like this with the buffer overflow attack. So the important point here is that the buffer overflow is not the only way to achieve the control flow hijacking. And we will learn how we can turn arbitrary read-write primitives to have a control flow hijacking. So you will see that at the end, arbitrary read-write would be the most attractive primitives to the attackers, because like it actually allows the attacker to do whatever they want. So to redefine the control flow hijacking, so if we can, it does not work. Yeah. Okay. If we can return, jump, call any kind of the control flow diverting instruction to any kind of the code, yeah, that the program should not execute, then that's the control flow hijacking. So the attack targets are, so the return address, if we use the buffer overflow attack, global offset table overriding. So if you do not recall what is global offset table, so I described that like there's a binary program and then it needs to be linked with the existing library. And then those library addresses are unknown, but at the runtime, if we call that function for one time, then DL resolver will put the function address into the global offset table. So if we change the content of the global offset table of printf to system, then printing sh will run system for you. Yeah, because computers are dumb, and then it just called the function pointed by the address. So this is an example that like without having the buffer overflow vulnerability, if we can overwrite global offset table, then we can hijack the control flow. And the global offset table is also one of the specific case of the thing, but the generalized version of the that name is the function pointers. So in the C or C++ language, we have a lot of function tables. And also, have you take a look at the disassembly of the switch case statement in C? Yeah, so that's quite interesting, because like if you have a switch case for like a 3 or 4 cases, then like compilation result would be the same as the compiling code that we wrote for if else those kind of the condition. But if you have a 16 or more cases in the switch case, and then how it works is like that it generates a function pointer and then try to jump to that function based on the number. Yeah. So if you implement the switch case for the number 0 to 15, then it'll be better to have a array of the function pointer and then just jump directly to that case. Then there's no if condition at all, right? But otherwise, it needs to go through like the if 0, 1, 2, 3, 4, 5, 6. Yeah, that could be like inefficient. And maybe you have thought about like that we can do binary search, so log n time would be like a log n number of the if condition would be sufficient. But having a jump table, yeah, would be much more efficient. So don't trust the source code. We must trust the binary, yeah. And then there are many places that like we can overwrite the function pointers and then divert to control flow, yeah. So that's the point. And for PLT, GOT, those kind of stuff, because for the program at the compilation time, we don't know where the library space printf will be located, because the same binary program will work for the VMCTF1 and VMCTF2, but the VMCTF1 is disabled with the ASRL, but VMCTF2 is enabled with the ASRL. So that means library addresses will be totally different, but we need to build a program that works for those systems. And how we do that is like we place PLT at the fixed location, and then it will have a GOT at the fixed location within the code. And then fixed location here means that in relative to the code address. So if the binary program is position independent, then the offset to the program code to PLT and GOT are fixed. Yeah. And because those information is fixed, what we can do is like whenever we make a call to printf, then we will generate the assembly for just calling the PLT part of the printf. And internally in PLT, what it does is like it will read the corresponding global offset table, fetch the pointer, and then jump to there. And then at the start, it will have a DL resolver address. So it will call that. And then after DL resolving the finding the printf, then it will put the address here, and we can call the real printf. And then I'm not sure one of you have thought about this during like taking this explanation. So if you have a ROP capability, if you can directly jump to the DL resolve, you can actually change the argument. So DL resolve actually gets a function name as an argument to resolve the address. And then if you change that name as a system, then it will just give you the system address. It will just give you an exact VE address. And then I want to show one of the paper. So I believe it's a feature, not a vulnerability. Yeah, but we can exploit that. So, title of the paper is something like weird like this. Then I need to share that over Zoom too. Yeah. So I like this research group from UC Santa Barbara because like these group has a similar characteristics that how I do both academic and hacking research, because this guy Giovanni Vigna, yeah, he is always competing in DEF CON CTF, and then like he founded the Shellfish team from UCSB, and then he won the DEF CON CTF one time. Yeah. I won 2 times, right? So that's why I always use better than UCSB. But the good thing is like how he guide all the students is, let me share it correctly, is like he teach CTF to undergrad and grad students, and then like they keep doing CTF again and again, and then raise their skill, and then at the end, not at the end, in the middle, in the meantime, they publish this kind of the academic paper based on the knowledge that they gain from CTF. Yeah. So the reason why I'm keep emphasizing that like, we need to learn every day and then do CTF a lot is like many students think that like the academic work is too difficult and then far from like an undergrad education or something, but I don't think so. Yeah, I've seen a lot of this kind of case, and then this paper is just about DL resolver attack. Yeah, and then so there's a PLT, and then there's a dynamic symbol, and then there are strings, and then if you change the string using arbitrary write or something, so it's something like before calling any kind of printf, if you change this into system and then call printf, then it will fetch the system address. Yeah. That's what this paper is talking about. And then like I will post a link to this paper into the calendar so you can read it afterwards. So although like it looks like somewhat academic paper, but these diagrams are like somewhat similar that I presented in the slide. So trust me, the paper is not that difficult at all. Yeah. So it's all about like the DL resolver will automatically fill our GOT. Yeah. Then like we can exploit that to launch any kind of the functions in the library space. Yeah. That's it. So, and publishing one paper as a lead author in like this kind of conference, you can get PhD. So getting PhD is not that difficult. Maybe I'm saying too much about like everything is easy, but indeed. Where's the Zoom? Shit. Right. So yeah. Then what is the required condition for the control flow hijacking? Yeah. So the buffer overflow for overriding the return address is just a one condition. So the reason why I'm keep saying this is like if we need to have a generalized idea, and then the buffer overflow is just a specific thing. Yeah. And then anything that we can override the return address, yeah, that will allow us to have a control flow hijacking. Any method with any method, if we can override the frame pointer, yeah, then that also allows us to have a control flow hijacking. Yeah. Then the capability that we need is actually the capability to having writing data to certain address. So without filling the buffer, without smashing the cookie, if we can directly overwrite the return address, yeah, that allows us to have a control flow hijacking. So that kind of capability is called arbitrary write. And the topic for today is like the arbitrary read and write. And you also you have already practiced some of the arbitrary read part. So in ASRL 1, 2, 3, 4, 5, you need to leak some of the address. And then the condition to leaking the address, it could be sequential leak from some of the stack buffer or buffer overread, something like that. But if you can read from arbitrary address, then that also conforms to the precondition that like we can succeed on like the avoiding the ASRL and launching the control flow hijacking attack. So basically, what we need is like the arbitrary read and arbitrary write. Then we can do whatever we want. Yeah. And then if you have arbitrary read and write, we can achieve the Turing completeness too. Yeah. So that means like that we can do whatever we want on the system. So we will talk about the new attack primitives. And then let's start with the arbitrary read. So arbitrary read is defined as a read from any address A for any number of bytes n. Yeah. So that is super general, a wider case of like the whatever we want to do, what we can do for arbitrary read. But in reality, the capability is a little limited than that. So either we cannot choose any address, but we can sequentially leak from the sum of the variable, or we can choose the address. And then also we cannot choose n number of bytes for the leak, or the n is limited by 64 kilobyte. And that's the case of the Heartbleed. Have you heard about the Heartbleed attack in 2014? Yeah. So yeah, then like the later in next week when we learn about defense, I will add like some of the depth parts to showcase like the what are the attacks in the wild and then how it was defended. Yeah. So I will introduce some of them. Yeah. So any address A, any number of bytes n is a more generic case, but in the reality, it could be n could be limited and then also A could be limited. Yeah. But with the limited functionality, even with the limited functionality, we can still do hack. Yeah. And then so examples of the arbitrary read could be read 100 bytes from the sum of the stack buffer address. And then if the stack buffer size is 80 bytes, then it might leak some of the return address or some of the stack cookie and those kind of things. And then if we can leak from certain address, then we can leak global variables, or we can leak a global offset table because we know the address. Then we can automatically know where the library functions are. Yeah. So we can use arbitrary read to avoid stack cookie. So we can read, we can have a sequential read from the stack. If we can do that, then we can leak the address. And then the reason why I marked as a not the circle is like the more triangle, not the cross. The reason is, so to leak the stack cookie, we need to know the stack address. But with the ASRL enabled, we don't know where the stack is at the first place. So if the condition is like not specifying the address A, but the leaking from the certain buffer from the stack, then we don't need to put the address. In that case, we can avoid the stack cookie. So that's why I marked it as a triangle. So it requires a more specific case to avoid the stack cookie. And then the same thing for ASRL. So if we know the global offset table address, definitely we can break the ASRL by knowing the address of printf, then we can know everything else. Yeah. But the reason why it has a triangle on it is that the case of the position independent executable. Yeah. In that case, we also don't know where the global offset table is. We need to leak the code address first. Yeah, that's why. And then the DEP, to avoid DEP with this kind of leak, so the avoiding DEP could be launching the rob attack. Yeah, right. And then to do that, we need to know the code address, and then like it will be reduced to the ASRL. So like the all triangle, but the implication is that the arbitrary read can help a lot in avoiding these defenses. So take an example of the stack cookie. So we have already learned about this one. And then, so we can specify n number of bytes to read from the stack, but we cannot specify which address it is. So in this case, for arbitrary read, A is limited to the near the stack buffer, but the n is arbitrary. So if we specify like a huge number, about like 200, 300, maybe 1000 or something, then it will leak the stack contents, then we can eventually see stack cookie value. And for this kind of thing, I don't want to call it as an arbitrary read. So like this is my own notion. Yeah. So I call it as a sequential read. Yeah. Because like we don't specify address, and then it leaks to like the memory space adjacent to like the target pointer. And we practice this kind of the sequential read a lot in ASRL challenges. So for example, in ASRL 3, we cannot specify A, but we can specify N. So we can leak many bytes on your call. And then this looks esoteric, but if you split it into 4 byte and then read it with the Pontoon script, and then for each 4 byte, apply U32, that's the inverse function of the P32, then you will have an integer value for all the pointer values. So with the arbitrary read, so actually the sequential read, if we can leak the stack cookie value, then we can launch the buffer overflow attack. Yeah. But to do that, we need to know the address of the stack as an arbitrary read. Yeah. So for breaking stack cookie, so some of the condition would not be met if you just have an arbitrary read. So that means like if you need to specify the address, you cannot do that. But in that case, how you can you can choose a different attack target, and then those cases are, if the binary program is not a PIE, position independent code, then in 64-bit, we already know that where the code is and where the GOT table is, then we can specify those address and read. Yeah. And then from there, we can take a look at where the library is, where the heap is. Yeah. If we find like all the locations, then so if you have like a capability of launching unlimited time of the arbitrary read, then you will eventually have the full view of the memory. Yeah. And then it's something like you are doing hacking, opening everything of the DRAM. Yeah. So this is the global offset table example. So you can manually read that with the read ELF, or you can use Pontoon to open the binary program and then the ELF instance and then e.got, and then use the dictionary to figure out where it is. But if you know the address, then you can easily leak those data with the arbitrary read. So after leaking the address value from GOT, then that will be any kind of function address in the library space. We can easily get the offset and easily get all the other function address. So the attack is not that difficult. And for the arbitrary read, I prepared 2 challenges for week 6. So SR1 is a sequential read, and then challenge number 1. Yeah. So the program will perform a sequential read. What that means is like it will let you know, it will leak some bytes to you, and you need to figure out where the targets are. Targets means like if you want to launching the ROP, then you want to find the gadget address, then you need to first figure out where the code address is. Yeah, because in this case, I enabled all the protection available in Linux. Yeah, so now it gets more difficult, but you will see that like the attacking this is not that different with the ASRL 1 or 2. Yeah. And then what you need to do is like from the leak, you need to identify like where the code is. And then you need to also identify where the stack cookie is. And then you need to break all the defense and call exactly in the libc space. Yeah. So it is combination of like a DEP1, ASR1, yeah, and then like the stack cookie 1. Yeah. Actually stack cookie 4, yeah, 1, yeah, that's okay. And then the next one is an arbitrary read 2. Yeah. So this challenge will let you specify the address. and then specify how many bytes you want to leak. Yeah. And then I believe this one is easier than SR1. Yeah. Because like if you want to leak if you can specify the address, you can specify any kind of the GOT address, and then this minor is not position independent executable. Yeah. So the implication is that if the full ASRL, including the code and data addresses, are also randomized, then you might need sequential read because you have no address information at all at the first place. But if the target program does not have the full ASRL, then you can know some of the address in the code and data, and then that stores the important data called the global of the table, then you can easily exploit that. Then by solving these two challenges, you will learn about the implication of the full ASRL and the non-full ASRL, and you want to enable the full defense. Yeah. And the next is arbitrary. Before moving to arbitrary write, any questions about arbitrary read? Yeah, it's all about the leak. Yeah, and then mostly like you can think it as like to break ASRL. Yeah, we need to know that, and then to collect the gadgets. Yeah, we need to know that, something like that. And the next is arbitrary write. So it just changed the read to write. So write on any address A and any number of bytes N, and that's the definition of the arbitrary write. Yeah. And then it also has a sequential write, but that does not have much implication. Yeah. So that I do not include like those challenges to not confuse you all. Yeah. But you can regard arbitrary write as like you can write this number of bytes to the somewhere in the stack. But what you need is just if you can overwrite 4 bytes or 8 bytes in 64-bit to return address store, then that's it. Yeah. Or you want to overwrite 4 or 8 bytes, depending on the bit width. If you can overwrite GOT entry, yeah, then you can win. You can directly have the control flow hijacking. So using arbitrary write, we can achieve control flow hijacking. So the important thing is like with arbitrary read, we cannot achieve control flow hijacking. So we cannot change the memory content with the arbitrary read. But with the arbitrary write, we can change the content, and then we can change the program's behavior, yeah, indirectly, yeah. And there are many ways, but to summarize some of the thing, we can overwrite return address, frame pointer, GOT entry, function pointer, jump table, and then virtual function table. And there are many places. Yeah. So the attack is something like you do a lot of recon with the arbitrary read. And then after finding the target, and then launching 1 or 2 arbitrary write, then you can get the shell. That's the more like the realistic attack. So we already learned about like attacking global of the table in ASRL 4 or 5. I'm ASRL, not sure. Yeah, it's ASRL 6. Yeah, maybe. Yeah. So if the binary program is non-PIE, then using arbitrary read to leak the address of the GOT to get the address of printf, and then replace some of the other function by overwriting the GOT entry, yeah, to the system address, then you can change the program's behavior. So even if the program called puts, exit, or those kind of function, it will go to global offset table, then you can redirect that to system. Exactly. Yeah. So suppose like you overwrite the printf the GOT to the system's address, then what will happen is, so in the normal case, if the program calls printf, it will jump to the GOT entry value, so it will call printf. But suppose you launch the arbitrary read to collect the data, do the recon, and overwrite the printf GOT entry into the system, then whenever you call the printf, it will call system. Yeah. Then this is how you can launch the control flow hijacking using the arbitrary write. So GOT addresses are known for non-PIE binary. And then, so the program will let you leak and write some of the values, arbitrary values, to any kind of location. Then you can find the GOT entry of the printf, and then you can also get the address of the system and then just overwrite that. And after you change the printf into system, then this part of the code snippet will not run printf anymore. So that will be replaced to running system with this string. Then what you should do is, first, you need to play with the path environmental variable to find the binary program first into your current directory. And then if you create a binary program named writing, then this code will run that program with the %lu bytes to %p \n as an argument. So if you override the GOT entry, then the function will be replaced. So you can regard the behavior would be something like this. And then the behavior of the shell is it will run the name of the program as the first one without having the white space. So we need to create the binary name as a capital W writing. And then we need to set the path environmental variable to refer to the current directory. And then this is why I inserted some of the function in ASRL1. Yeah, you can practice that with the ls execution, and then later you can use that in that trick with the arbitrary write. So for the arbitrary write one, AW1, yeah, you need to change the GOT entry of the printf, and then override that to execute me function. Yeah. Then the execute me function will grant you to get the privilege and then running the shell. Yeah, and then that's it. And then for arbitrary write 2, you need to, the program contains both arbitrary read and write. So using arbitrary read to leak the GOT entry, and then leak the printf address, calculate the offset to get the system address, and then replace that. Then the printf will be changed to this execution like this. Yeah. So these are the things for today. And then on Wednesday, after practicing arbitrary read and write, we will use printf as another gateway to let the attackers have the capability of the arbitrary read and write. Yeah. So to give a little hint, so if we can inject this kind of the percent directives to the printf function, because printf will expect there will be some of the arguments to there, and then there's no fixed number of the arguments available for printf. We can actually have an unlimited number of arguments, and then if you can inject a lot of percent related variables in there, then we can actually turn printf into the arbitrary read write primitive. So we will learn about that on Wednesday, and then before that, we will practice arbitrary read and write, and that is hosted in VMCTF2 because I need to enable all the protection for some cases. And then all the challenges are week 6 directories, so please start with the fetch week 6 first. Yeah. And then the due date is March 8th, so we will have plenty of time for that. But I know that some of you are still struggling with the week 4, 5, 6. So yeah, so take your time to solve that first, because without having the good knowledge in the week 4 and 5, week 6 and 7 could be difficult. Yeah. Any questions? I believe you will have a much more question after you take a look at the challenges. Yeah. So let's do that. But before starting, I want to show one thing. So I created like these many of the challenges, but each of challenges will ask like a very specific thing, and then the conceptually, what you need to do is very similar to AW2 for all the other challenges, right? So if you can solve a AW2 correctly, then I believe like you can solve all the rest of challenges over here. Because like the format string read is like the sequential read using printf. Format string read 2 is like arbitrary read using printf. And then arbitrary read is like the arbitrary read with the printf. Arbitrary write with the format string is like the prefixing AW2. Yeah. And then code execution is the same as AW2. And then code execution PIE 64 is like it has like the 2 leaks and then 1 write. Yeah. So 1 sequential read, 1 arbitrary read, and 1 arbitrary write. Yeah. So like it's a 1 step further than like AW2. Yeah. And then the reason why I set the higher points for these ones are like these AR, AW, SR. Yeah, these are like more like a primitive and foundation. And then format string challenges are more realistic. So you will have a much more fun after learning like what we can do with the printf on Wednesday. And then another fun thing is like I released the extra credit challenge. So for this challenge, you will have a no binary program given. And then what you can do is like you can just connect to the certain port. Then it will give input and output kind of thing. So you can just interact with that. And the challenge is that from there, you need to leak the binary content first. And to do that, you need to know where the code is, because like this one is like the PIE is enabled, NX is enabled, canary is found. So I enabled all the protection. So you first need to learn where the code is, and then you need to learn the entire content of the binary program. And then you need to reconstruct the binary program to do the reverse engineering on it. Then you can find the vulnerability inside of there. Then you can launch some of the attack to get the shell. But this is feasible. Yeah. So like that. But please don't try if you cannot solve like some other challenges. Yeah. So your time is much worthful when you take a look at the other challenges. So if you finish everything and then just focus on like something more, then please tackle with this challenge. And then a few years ago when Lucas was taking this class, so there is one guy, oh, I successfully steal the binary. And then can I put that into the temp directory for all students? Yeah. And then I let him play like a Robin Hood. So some of the students like just get the binary from the temp directory, but to have an extreme fun, yeah, please, if you want to work on this challenge, then please work on like leaking the binary content first, and that'll be fun. So the implication of this challenge is that even if we have a full protection on the current era, if there's a vulnerability in printf, then hackers can own the system and then get into there and then do whatever they want. So any kind of single mistake is super dangerous, even if we enabled all the protection. That's the implication of this challenge. Any questions? All right, then on the course website, schedule site, schedule page, there are some of the tutorial videos, so don't forget to watch that. And please work on the challenges, and please ask any questions to myself and Lucas.